Millions of players log into Dragon Arena every day to battle for global dominance. It's a highly competitive multiplayer environment where prestige is everything. To maintain that competitive drive, the back-end system has to meet three strict functional requirements. First, the interface must continuously display the global top 10. Second, any individual player must be able to instantly pull their exact absolute rank out of millions of users. Finally, the system needs to return a relative rank. A player needs to see the 4 competitors immediately above them and the 4 immediately below. If a player spends hours defeating a raid boss, checks the leaderboard and sees an outdated rank, the competitive illusion shatters. The system has to reflect reality instantly. Translating those gameplay requirements into back-end mathematics reveals the actual scale. 5 million daily active users, divided by roughly 100,000 seconds in a day, gives us a baseline of 50 transactions per second. But server traffic is rarely perfectly distributed. To account for prime-time evening spikes across different time zones, we multiply that baseline by 5, raising the threshold to 250 peak transactions per second. We then factor in the gameplay loop itself. If each user plays an average of 10 matches per day, the server needs to safely process 2,500 write queries per second during peak hours. The storage footprint for this data is surprisingly light. Saving an ID and a score for 25 million monthly active users requires roughly 650 megabytes of memory. The storage isn't the problem. The complication comes from how we secure those updates. We have to assume the game client running on a player's smartphone is entirely compromised by potential attackers. A player's device cannot be allowed to dictate its own score. An authoritative game server has to independently validate every single match win before issuing a score update to the leaderboard. The core engineering challenge is safely processing high-velocity, continuous rank updates under intense write pressure without introducing any noticeable latency. The standard approach to storing structured data is a traditional relational database. A basic schema for this looks exactly like the table shown here. Millions of rows, each containing a player ID and a score. Fulfilling our first functional requirement, finding the top 10 players, is easy. A standard index can quickly return the highest values at the top of the table. The bottleneck hits when we try to fulfill the second requirement. To calculate the absolute rank of a player stuck in the middle of the pack, the database has to scan and count the exact position of millions of constantly shifting rows above them. Running those heavy counting operations while simultaneously writing 20,500 new scores per second overloads the CPU of a standard database server. The query times balloon from milliseconds to tens of seconds. Relational databases are highly optimized for durable, persistent storage on disk. They are completely the wrong tool for the real-time, continuous resorting of millions of records. The industry standard for real-time ranking is an entirely different architecture, Redis sorted sets. Redis operates entirely in memory, bypassing the heavy mechanical latency of writing to a physical disk. As illustrated here, a sorted set isn't a single entity. It maintains 2 distinct data structures in parallel, a hash table and a skip list. The hash table handles direct lookups. It provides constant time access to map any specific user ID directly to their current score. Meanwhile, the skip list organizes the rankings. Instead of forcing the system to sequentially check every single node, it builds a multi-tiered hierarchy of express lanes. When a new score arrives, it jumps across the highest level arcs to rapidly narrow down its location, then drops into the exact correct position. The entire operation happens in logarithmic time. By pairing a hash table with a skip list, Redis shifts the heavy computational lifting. It sorts the data at the moment of the write, so when a user requests their rank, the answer is already waiting for them. We can now map the game's functional requirements directly to optimized Redis commands. When a player wins a match, the game server sends a post request. Redis executes a z-increby command, which instantly increments the player's score in the skip list, or creates a new node if they haven't played before. To render the global leaderboard, the game fires a GET request. Redis uses the z-rev-range command, reading the data in descending order and instantly extracting the top 10 players. If a user needs their specific global placement out of millions of players, the system executes z-rev-rank, pulling their exact numerical position in logarithmic time. And to find those nearby rivals, the system uses a compound technique. It finds the user's exact rank, then executes a Z-rev range with an offset of 4, returning the immediate competitors above and below them. The intense mathematics of continuous ranking are entirely abstracted away. The application code just executes purpose-built commands against an optimized memory structure. Viewing this system flowchart, we can track the complete journey of a match from the player's phone to the data store. The untrusted game client pings the game service. The game service validates the match logic, strips out any tampered data, and securely passes the verified score to the leaderboard service. The leaderboard service then executes the commands, writing the rank update directly into the Redis node for immediate read access. Relying entirely on memory is a critical vulnerability. If the Redis server loses power, the ranking history evaporates. To recover, the system needs a source of truth. The leaderboard service asynchronously writes every match outcome to a durable MySQL database. At the end of the month, a scheduled cron job provisions a fresh, empty sorted set for the new tournament and archives the historical data. Production architecture balances the extreme speed of volatile memory against the unshakable safety of persistent disk storage. If Dragon Arena goes viral and the player base suddenly spikes to 500 million daily active users, the baseline metrics completely break. The memory requirement swells to 65 gigabytes, and the peak write load hits 250,000 queries per second. A lone Redis node becomes a single point of failure. It will exhaust its CPU and memory limits attempting to process that volume of traffic. Sharding partitions data across multiple servers. Hash partitioning distributes load evenly, but finding top players requires querying every node and sorting results locally. Alternatively, fixed partitioning divides servers by score ranges, making top 10 lookups effortless, but requires migrating players between servers as they advance. Engineering at massive scale rarely reveals a single perfect algorithm. It requires analyzing the constraints of the data and choosing the exact right trade-offs to keep the arena running.